Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Glacier, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you. I'm trying to catch up on some of the outstanding videos that I promised to make based on some of the comments I received. So one of the comments I received was the issue of snow cover. And I did a number of videos on snow cover, but I can remember in that videos using a data set a number of data sets, but I can remember by myself, none of them actually talks about the depth of the snow. It says there's snow, etc., etc., the chances of there being snow and where the snow is and all of these sort of things. And I used elevation models to determine the height and temperatures and all sorts of things. But what was interesting that none of these data sets that I used actually had snow cover as depth, the depth of the snow cover or the density of the snow cover. So I left it there, and then when this comment came through about snow cover, I thought, this is interesting. Fortunately, and this is whether call it luck or call it, I don't know what you would call it. Just before that, I had somebody asking me about rain and temperatures and things. And the normal one that I use only had it until 2023. There's nothing for 2024. So I found this data set on the catalog that had temperature and rain up to 2024, which was good. But within that, it also had snow cover or snow depth or snow density. And I thought, geez, I was been, I should have, I wish I knew about this data set when I did the snow series of video tutorials. Anyway, a day or two later, by hook and by crook, I got a comment to say, please, can we do something on snow depth or snow density? And so, voila, I knew there was a data set, and there we went. So this is what basically transpired leading up to helping on that specific comment. So it just shows you, just shows you. And there's such a lot of things in that catalog that one don't know of. Anyway, this is part of this video tutorial, is to explore these data sets and to see what is available in this catalog. So that was one prepared, so when these sort of comments or questions come, we know where to go. Anyway, so this is then the result of this. Okay, so remember, this is this data set. Let me just go there. Where's this data set now again? Anyway, we'll get to the data set. We'll get to the data set, but it basically gives you snow cover. So that's not that one there. This is this one here. Okay. As I said, didn't know this thing exists. Not data platform. Didn't know it existed until I got that request for the temperatures and the rain and all these sort of things. So there it sits. So within this data set, you'll remember these ones. I think it's 158, 159, 160. I think it's these four, if I'm vaguely correct. I think we use this data set, this one here. And if I went for the bands, I see, remember there's the temperature one, etc. And I see there's a lot of interesting things here. Soil temperature, lake ice depth, lake ice temperature. Now, my region of interest, there's no lakes. So these things are, and there's snow. But look at this. There's my snow cover and my snow density and snow depth. Instantaneous grid box average of snow thickness on the ground. Mass of snow per cubic meter on the snow layer. So there's two So snow covers is yes or no. Okay, so that's fine. But this is two ones that I was unaware of. I wanted to do this in that series. Let me just go back. When did we do this series? Let me just go back. Sorry. Let me just refresh my mind. We did something. It wasn't that long ago. Because that series was also inspired by some comments or questions. I don't know exactly where it was. I think it's, there we go. Snow cover. There we go. Terra snow cover. It was what was it to do. It's from here, from 6.5. I think 6.5 to um, I think basically to 7.5. No, even further. These ones here. So there's a number of them, but none of them, if you go back and you have a look at them, none of them actually does about snow depth or snow the cover itself. And that's because the data sets that I used then didn't have this function or this band. And this data set fortunately does have the band. So as I said, coincidence? Who knows? But anyway, so there's this artificial glacier. This is in the north of India. This is in the north of India. There's this glacier here. Okay, let me just zoom out a bit. So just for a bit of reference, um, see this is India here. So it's in the far north of India. Sort of, here's Afghanistan, Tajikistan there, and we have China here. So this is basically India there. This is India. So this is in the far north of India within this triangle. So if we put the satellite map there, let's go look at that. You'll see there is the glacier here sitting there. And apparently this is an artificial glacier. The glacier is made to capture water for the people that live here because it's a very dry and ragged area. That's my understanding. Although, as I said, I don't know for sure, but that's what I've read. So you can see there's the glacier. It sits here. And apparently, it's artificial glacier. Okay, so it's the north of India. Okay, so there it sits. So if we keep it, so the person wanted to know. Okay, so if we drill down, there's a river. The person wanted to know the snow cover of this particular artificial glacier. Okay, that's what the person wanted to know. So obviously this is low level, low lying, low lying areas. So most probably there's gonna be very little snow. It's most probably around here. You can see the snow in these sort of mountains. That's quite thick snow here. It's quite a smallish area. My region of interest is not very big, so it only captures a small part of this ecosystem or the snow system here. You can see it's very rugged. Um, that anybody can stay there is actually interesting. Wouldn't say it's a miracle, but it's interesting that people would want to stay there, could stay there and make a living. If we go in, let me see. There seems to be a bit of a village there, but let's just take this away. Well, I don't know whether yeah, there seems to be a village. Yeah, there's a village here on the below side of the river. So there's definitely a village lying there. You can see some agricultural areas here, some low-lying agriculture, and you can see there's a road there, etc., etc. So that's quite interesting. There seems to be a fairly big city around here as well, or town or settlement. So there's definitely some settlements here, but as I said, it's in the lower areas is where these rivers sort of mouth or where there's water. And so seemingly the communities that live here is very much dependent on the water from this glacier. Um, yeah, so the the livelihoods and the welfare of these people living around these sort of areas, low-lying areas, are basically dependent on the water and the water obviously comes from the snow, comes from these glaciers. So no glaciers, no water, hardship, and vice versa. Okay, so that's basically the what was asked is what's happening with the glacier. Can we trace the movement or the trends in the glacier? What's happening here? So that is what the question was, or what the comment was. Okay, so first of all, what I wanted to do, let's quickly remember this satellite now is for whenever this was done. It doesn't actually say when this image was taken or this satellite image or picture was taken. So let's go back to our map and stuff. So now, obviously, for daytime imagery, to visualize this over time, we can again either use Landsat or we can use Sentinel, depending on how far you want to go back into time. Because Sentinel, unfortunately, is limited to 16, 17, 18, where obviously Landsat you can go back up to 1970. So that's your first question: is for what period am I looking for? Am I looking from 1970, then, or much earlier than 2016? Then Landsat is the preferred option. If you say, no, I'm only interested in the last couple of years, 4 or 5 years, then I would suggest using Sentinel. If you want very higher resolution, then Sentinel. If you are okay with lower resolution, not bad, but lower resolution, then I would go with Landsat. So Landsat is, I think, 30 square meters, where Sentinel, I think, is 10 square meters. So Sentinel, much better in terms of its resolution, worse when it comes to its time. And Landsat is the opposite. Okay, so that's just quickly. So first thing I wanted to do is to generate. So fortunately, the person didn't want to go too long back into time. The person was happy with 2018 to 2023. Okay, so that implied, but obviously snow is quite a, yeah, snow is, yeah, so it required a high resolution, and that's why we captured Sentinel. If it was like temperatures or things like this, I would have gone, then resolution is not that issue. So what you want to visualize will to a large degree tell you the resolution, the spatial resolution. Anyway, okay, so first of all, our region of interest. Okay, there is our region of interest. We've loaded it. We add that region of interest to our layers or to our images. We center it around that, and we create our clipping function. Now this should be standard practice. And then, as I said, we just load our Sentinel images. Now the script for Sentinel images is not just the image itself. Because of clouds and all of these things, we don't want images with clouds, and so we want to mask the clouds out. So there we masking the clouds out. I'm just defining my region of interest, and there is my, and then obviously I'm going to have it for defined period for multiple. I want to create a looping function for multiple images, and that's why I say I'm not putting a start or end date within the filter. I'm saying I'm going to define it later. Okay, so there is get your yearly. So now I start my script, and this is a loop function, meaning it will loop until this part here. You'll see it opens there and it closes there. It doesn't close there because there's no comma point. So it closes there. So this is one part. So this is the loop. So it will keep on looping. It will keep on looping through this for all of the years. For the years. Okay. So get yearly composite. That's just the name of it. Because this I think is monthly. Yeah, monthly. Okay, so I want it for a particular year. So it's image, it's 12 images per year. So we need to reduce it. Okay, so that's why I get yearly composites. So we're going to get a composite for each year. And that composite could be a mean, median, sum, whatever the reducer we're going to use. Okay, and we're going to take it from all the images. So the start date will be the year. Remember what is going to be our years? There's our years. So it will automatically select the year, and then 1st of January till the end of December. So it will take the whole year. So all images within the year. Okay, so it will take all images in each year, starting from the beginning of January till the end of December. Okay, so if you want it only for certain, so only net from say for June and July, then you'll just convert this to June and July. So that will become 5 and 6, for example. Or if you want to, yeah, so just manipulate these numbers or these variables within your start and end date to either increase the number of images or decrease the number of images for your year. Okay, so that's basically what we're saying there. So we're going to create a composite, and that composite will be on a yearly basis. It will do for each year. Okay, and each year will start from the beginning till the end of the year. Okay, so not half a year, specific months, etc. And there's our Sentinel data set, harmonized Sentinel-2. There's our start and end date, so that's going to loop the whole time through this. We only want images with a with cloud base of less than 20%, and we're going to mask out clouds, and we're going to clip it for our region of interest. Okay, so this should be all still fairly familiar, and then we're going to create a median image. Okay, so that's all it. So it's going to loop the whole time through this. Okay, so next step is we're going to say what is our years. The years that we want is 2018, 2019, 2020, 21, 22, 23. So rather than creating 1, 2, 3, 4, 5, 6 scripts, copy and paste, copy and paste, copy and paste, just change the date, we're just creating this looping function that automatically runs through this. Okay, and it will run for, as I said, it will run for each year. Okay, so the years for each year. So that's why I said it will run for each year within this years variable. So the years variable is these, and these are years, so therefore it will run for each year. So there's our looping function. Okay, there's our looping function. This is our visualization, our standard visualization. Is it red, green, and blue? Is that the bands? Red, green, and blue? Yeah, red, green, and blue. And then we're just going to add it, our yearly image, visualization parameters, and then RB plus the year, and the year being each of these years through this looping function. So I hope that makes sense. So we're generating basically this. These 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 images. And this is a datetime image of our region of interest using the red, green, and blue bands. Okay. And let's wait for it to load up. You can see the snow area. You can see the snow. You can see the lower lined areas. Okay, as we've presented it earlier, there's these rivers. Remember, there's a community there, there's a community there at these rivers, and you can see the streams, the water coming down from the glacier. There's a big one coming down, filtering in here. There's one filtering there, and that's why these communities are downstream, because they then use the water that comes from this part of the glacier coming down into the stream, and from this part coming down into the stream. So there is. So let's have a look and see if we can see how this have changed over time. So that is, okay, 2018, for whatever reason, there's nothing there. Don't know why. Because there's 2018, so I'm not sure why 2018 is not giving us anything. Because there's definitely stuff for 2018. Anyway, 2018 is nothing. There's 2019. 2020. Ooh, look at that. 2019 and 2020. 2020 is much less snow than 2019. 2021, the return of the snow. 2022, much more snow. 2023, much more snow. So it seems like the last 3 or 4 years, there's definitely been an increase, significant increase, if I might say that, in snow cover. After a number of years, I mean, if you compare, I don't know why 2019 doesn't want to. If you compare 2019 with 2023, you can see it's chalk and cheese. Huh? 2019, very little snow. 2023, lots and lots of snow. So that just gives you a visualization of the snow. Okay, so you can say there was snow, but it actually doesn't tell you the depth of the snow or the density of the snow, the volume of snow that has fallen. Okay, so that's something that we need to sort out, is actually how much snow. Is it just very light, very thin, little bit of snow, or is it significant snow? Remember, this is the average for the whole year. Oh, sorry, we're using the median. Sorry, the median. That would include the wet season and the dry season, the warmer season and the colder season. So typically what we most probably would a better option would be if we do this for just the winter time. Oh, interestingly, for the summertime. And we'll just change this. Now we need to figure out when is the rainy time in that part of the world. I don't know. We'll have to find out. There's some density, so that's, you can see that's July. So it seems like the high place is July. So this is snowing, and that will be obviously then December and February. Yeah, so that's winter rainfall and summer dry season. So summer is June, July, January, February, March, December, November, December, January, February, March. And winter is then April, May, June, July, August, September, thereabout. So we can change this to just do summer, or we can change this just to do winter. Again, that's up to you. I've just done a median for the whole year. Okay, so there's just a time series. Okay, so this doesn't tell us much. Doesn't tell us it. Well, let me not say it doesn't tell us much. It tells us a lot. But it doesn't tell us the snow itself, the thickness of the snow itself, or the density of the snow itself. Okay, so, but again, useful to use a looping function. Useful, very, very useful to use a looping function. It will loop through these 6 years without, yeah, so you don't have to duplicate. I'm not sure. You see, the problem is, although this is Sentinel now, and it's the same as with the location that I am, my region of interest. Come on. So although Sentinel says there should be data available, for my specific region of interest, there is nothing available. So that could mean that for that specific reason, location, there wasn't Sentinel data available. You see, it starts in 2017. So theoretically, there should be. But we know that in some places they don't. They only start much later. So that simply could be that there is no data available for 2018. Well, there is no data available or Sentinel image available for 2018. So if you wanted to go back into time, as I said, there's no way you can do it for Sentinel. You'll have to do it for Landsat. But Landsat wouldn't give you a nice resolution. Maybe we can do Landsat and see what the difference in the resolution looks like. That would be interesting. Anyway, let's park it there for now. Okay, so that's now. So now we've got this. So now we can basically visually say 2018, 2019, 2021, very little snow. And then from 21, snow started increasing up to 2023. So definitely been a significant increase in snow. So that is clear. Then I thought, okay, let's just also then just compare this with our MODIS snow cover data set. And that's derived from MODIS. So if we go there. Now that is just, again, just to, oh, why am I doing this now the whole time? I should go to data set. And I go to search, and I go data set. I copy the data set in. And it should, there we go, Terra Snow daily cover from 2000 to 2024. Snow cover, but you see, it doesn't say. It just gives you a minimum. It's not, it just provides values on mask out. So just say whether there's snow or not. To a large degree. It doesn't tell you much, but it should collaborate. It should confirm our, well, it should back up. Let me not say confirm because this is derived from Landsat most probably. It just backs up. It should just back up our Landsat images. So we do the same. Also a looping function. This case 2019. Why did we not do 2018? Why didn't we do 2018? Hmm? Why didn't we do 2018? So let's do 2018. At least we have something for 2018. I'm not going to run it now because it's going to take some time to do it up. So let's quickly have a look and see. Now, most probably why I didn't do 2018 is because there's no corresponding land. And we didn't do 24 because the problem is this, it will want to seek it until the end of 2024. It's not going to work. But we can put in 24 and let's see what happens. Okay, so we can, before we run it, let's quickly go it and we will run it and check. Okay, so that's basically just this data set. We select this, same as started, we clip and we just create a looping function and it will generate those 4, 5. And there is the minimum maximum value, the color palette, and we just display it. So let's have a look and see how that looks. Okay, so let's go 2019 and 2019. Okay, so that is according to Modus. That's what I'm saying. So that's supposed to take long because it's a very small region of interest. So I'm not sure why it's taking that long. It's Hanaing again. It's so frustrating. But you can see there's a snow cover. Let's zoom in a bit. Let's zoom in again. I'm making it even more problematic. And there's the Modus. Eventually. Anyway, point is, it overlays pretty nicely. And these numbers give you some indication of whether the ice is thicker or not. Doesn't tell you how much thick or how dense the snow is. It just tells you there's more snow or there's less snow. It doesn't tell you about how much or by this or by that. So it's an artificial number. Okay, so but you can see it gives you there in the higher areas there's more snow, in the lower areas. But it almost perfectly overlaps with the snow. So that's 2020. Let's go 2020. There is the snow cover according to Modus, and there is the snow according to Sentinel. Okay, so let's go to the most newest. There's the snow cover for 2023. We know there's a lot of snow, and then there's the Modus for 2023. Eventually, it's not supposed to be. You can see how much more snow there is. You can also see it's seemingly much more of these dark areas, meaning higher snow values than lower snow values. So there they are. As I said, there's and it's not gonna, there's the snow for 2019. You can see the shrinking in 2020. I really don't know why it's taking so long because it's a very, very easy data set. It's a very small region of interest. It's really supposed to go very quickly, but Who knows, the internet might be off, whatever the case might be. It's very, but yeah, let's give it some time. Okay, so that's that. So while we're working on it, then we're generating a time series chart. Okay, I'm generating a time from snow density. Let's go back here and see what snow density is. Snow density is kilograms per cubic meter. Mass of snow per cubic meter in the snow. So that gives you how much, what is the volume of snow. Okay, the EM integrated model represents snow as a single additional layer over the uppermost soil level. The snow may cover all or part of the grid box. Now let's just quickly have a look and see. You see, it's quite a high resolution, like a low resolution. Sorry, so it's not. Yeah, let's leave it at that. It's not ideal, but snow normally covers quite a large area, so it's not finite or very granular snow area. So we could work with this. Okay, so we've got this, we've got our band, and we say let's listen. There's a scaling. There's no scaling factor. I've incorporated just for, you'll see some of them do have scaling variables. If there's a scaling variable, we've built it in, but now we're just going to use one. So we're just going to multiply by 1 because there's no scaling to be done. Our start date, our end date would be the beginning of the data set. So we're not confining it to another period. You'll see there it's 1950. So there we go. That's 1950. And then we just generate the time series and we print it. Okay, we generate the time series and we print it. Okay, and that's basically that. Where's I'm now? Okay, and that's basically it. So if we open it, there it is. So you can see, again, one will have to put it into Excel and play a little around in Excel. You can see seemingly the period that it had the least amount of snow was, you see the snow density was 122 kilograms per what cubic meters. Because remember that's cubic meters, so it's 122 kilograms per cubic meter. That was in 1952 when it was the highest. Seems like it was there. 1969, it was the highest, which is 445 kilograms per square meter, a cubic meter. Has it come? I don't know. There seems to be some. There's a period here where there seems to be much less snow, but so that's definitely seeming a period. There seems to be an upwards increase here, and I just basically very roughly with my eyes, increase period here, decrease period here, and then it seems to be starting to increase again. So it's definitely starting. Yeah. So is it significantly lower than previously? No. Is there significantly less snow than past years? No. Is there significant more snow than past years? No. Looks very stable. Yes, you have a outlier here, outlier there, but it's normally not long term. You don't see 3, 4, 5, 6 months of we see maybe a year or 2 years where there's abnormal snow, either good or bad, on the upper side or the lower side, but in general it looks fairly stable. So has the snow on the glacier increased over time? No. Has the snow on the glacier decreased over time? No. It has stayed fairly stable with the provision that you have now and again a yearly anomaly, either the good side or the bad side. So this is what I look from this. Okay. Then the question was, okay, can we visualize the changes? Can we visualize the changes between, let's say, the last 2 years? Okay, let's say the last 2 years. So we've created a script here which says, where is it now? Let's just get it. Yeah, here we got. and we generated a script the old-fashioned way for 10th and 11th month of 2023. Let's call it October 2023 and June 2024. And we both medium, and then we basically just create a temporal difference where we subtract it. Now, remember, this is each of these has 3 bands. Okay, so we have to subtract all 3 bands from one another. You see, there we subtract band 4 and band 4. There we subtract band 3 and band 3. And there we subtract band 2 and band 2. So therefore we have a temporal difference image for band 2, temporal difference image for band 3, a temporal difference image for band 4. So we have 3 temporal different images because Sentinel is multi-band. You don't have to do all 3, you can just do, but I wanted to have a look and see what the 3 looks, and this is basically what the 3 looks like. Okay, so the red, so if we go down, okay, so that's the export function. So the red is minus, the white is very little change, and the green is more snow. And the green is more snow. So what this means is that these locations recorded significant decreases in snow cover or in snow compared to the green, which recorded increases. So that is, which one is this? That is band 2, that's band 3, that's band 4. So all 4 bands roughly indicates the same thing. Very roughly, but so this implies that from June 24, from October 23 to June 24, there's been a significant decrease in snow in this area. Now, this is purely because we choose these dates. We choose these dates. Because October is coming out of winter. So therefore there should be more snow. June, we're coming out of summer. There should be less snow. So it's obvious why this looks like it is. It's got nothing to do with actual long-term trends or things like that. It's purely because our selection of these months, our selection of those 2 periods, which is a terrible collection or decision because you don't do June and October. What would be the point? You will do June and June, or October, October, or something to that effect. You don't do these sort of ad hoc months because you're going to have skewed results because, as I said, we know and we've seen that if you look at this, you look at typically where's a June? June is a fairly high month, but it's not as high as October's. Where is it now? We actually need to put it, I've put it somewhere in Excel, but I can't remember where in Excel. So let's use inspector and press there. Okay, so we're not going to go for that. I'm not going to go for that. Not going to go for that. That's not going to go for that. Okay, so there's the snow cover. Not going to go snow cover, blah, blah, blah. Let's see that the difference is 0.65, 0.68, 0.62. Snow cover, but we don't, yeah, that's yearly number, so we don't have it, so that doesn't help either. But June is typically a high month. You can see that June, July is typically high, and then October. There's March, was October. I'd love to see where October is. Okay, there's June, July. See, there's October. So how can you compare that? So that's why there's a difference. That's why there's a negative, because you take a high month and you subtract a low month. So obviously you're going to get all this bad. So you see there's October's are here. So October's on the low end, and June and July are on the high end. So this actually makes absolutely no sense. But anyway, it shows is that if you do it that way, there's then you will find this. So it actually should be okay. So yeah, so that basically, and then obviously we're going to export these images. We're going to export the each of these images. Yeah, there's our scaling. That's our yeah, region as our region of interest. That is our file, the folder. We just need to put in the folder there, and the name of the file that we're going to save in the folder. So that's for October 2023. That's for June 2024, and that's for band 4 difference between the months, band 3 difference, and band. And the idea was if we take these bands, these temporal difference, because there's 3 of them, we put it in QGIS, we run it through um, virtual raster, how that would look. So that's why we wanted to export it. So this is quite a neat little yeah, program. Once again, it showcased looping, the loop function, so which is always beneficiary. It shows how to loop so that you don't have to write long or copy and paste and copy and paste and copy and paste. You just create the loop. Second of all, it shows snow level. It captures snow quite significantly. It shows you how snow have changed over time. It gives you the dynamics of the snow, the seasonality of snow. We can create temporary difference images to visualize the areas that recorded increases or decreases in snow, etc. etc. So this is quite a neat little program. A neat little program that, again, you can apply to other data sets, etc. etc. Okay, cool. So I hope that helps. As I said, it would be interesting. Let's just run it and see. It would be interesting to. I'm just going to put that. Remember, why did we put in 2018 there as well? To see how the 2018 compared and 24. We're not sure if it's going to show. There's the 2018 one that we've added here, because remember that 2018 doesn't work. Anyway, there's our normal time series chart of. You remember this time series is for the whole area, ne? We actually, which includes these areas that recorded no snow. So this is a significant underestimation of the snow. So actually what we have to do is create locations, point locations or polygons in the snow area, and then create charts for those areas. And we can do that through the looping function as well, where we have another table on asset, which includes all these. We can just use our function here, new layer, etc., etc. And we've done a number of videos on it. So we can typically cluster them around non-snow areas and snow areas to see statistically if there's a difference. So there's much more than we can do with this than what we've done now. Much more than this. But as I said, you always have to start somewhere. And as I said, once you're here, the next set of ideas comes along. The next set of ideas comes along. The next set of ideas comes along. And so you keep on building and expanding your script. Okay, but understanding that script must have limitations. Otherwise, you're going to run into uploading time errors and usage errors and all of these sort of things. So, yeah. Okay, let's park through there. That is this particular comment, how I helped and addressed that specific question about the dynamics, the changing dynamics of snow on that artificial glacier. Cool. Let's park it for there. Okay. Boys and girls, remember to subscribe, to share, to link, to send some comments. I will respond to all of them as soon as I can. So, yeah, keep them coming. And if you have ideas, send it. I always try to get to work on these ideas. There's 2 or 3 more that I've put on the back burner that I'm going to see if I can address them, which were also interesting comments. So let's work for them. Let's make it happen. Let's make it happen. Yeah. So with that said, I'll see you on the other side.